31 is 2/3 x to the 4th. Is that the one you're talking about? 2/3 x to the 4th. Describe how to obtain the graph of the given monomial function from Great Day, Stacy. Well, what's happening here? Compare it to x to the 4th. This is compare it to the graph of x to the n where n's the same power. What's the difference? How do I get from this one to this one? What's being done? It's a vertical shrink of 2/3. Yeah, that's it. That's all you had to do there. Vertical shrink of 2/3. So if it's vertical, it is what it is. If it's horizontal, it's opposite. Yes. Yes. Okay. How you know what? So because it's in front like that, if it did this, that would be horizontal. What else on your homework? $25. N equals C over V, where N is the refractive index of a medium, V is the velocity of light in the medium, and C is the constant velocity of light in space. So that's important. That tells me this is the constant. And it says to write a sentence that expresses the relationship in the formula using the language of variation or proportion. So all this is saying is that N is inversely proportional to V. This is where we talked about inverse or direct variation. This is inverse because I'm dividing, or because this would have a -1 exponent. So all you have to say is that N is inversely proportional to V. Yeah. It's same thing. It's just different. Yeah. If you have a constant, so if you can rewrite it where your variable has a negative exponent, that's inverse. Oh. Same thing with the variation. It's okay. Well, they could all be written as proportions. You can always write them as a proportion. It's just a division. So even if you're multiplying, you could solve it for k and write it as a fraction. What else? Yeah, you would just say n is inversely proportional to v. Which ones did I give y'all to do?
1 through 7, 1 through 9 on, 17 through 47. I don't know.
So match the equation to one of the curves labeled in the figure. And this was a non-calculator. Oh, what? He used his calculator. What did you just do? What did you just do? Did he use his pinky? It's kind of the same. All right, let's look at them. I've not been on my game today. I'm sorry, y'all. Thank you, Carter. You're so supportive. I appreciate that. Why is it not launching? Therapy. We need therapy. We'll see. All right, polynomial functions. Not today, though. We talked about. Is there comfort colors? Polynomials. We focused. No, I just slid it over. We dug into linear functions. We dug into quadratics. Now we're going to look at higher degrees. Things like cubics. Cubics have a degree of what? 3. How about quartics? When we're written in standard form, back to polynomials. When we're written in standard form, remember that funky way we wrote them? A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus da, 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 da. No. 2.3. 2.3. All right, so if this is my polynomial, tell me what a sub 0 is called. Okay, but what is it? It's called something else. Constant. That's what I was looking for. Constant. But it was the wrong one, so it doesn't matter. Constant. How about a sub n? Which coefficient? The leading coefficient. This is called the leading coefficient. How about the n? Degree. Is that good? You might be a little taller than them. Y'all got that? Okay. Great. Okay, tell me when you're done. Oh. You are full of crap. You're not writing this down. You're just doodling on your paper telling me you're not done. What's the degree? Leading coefficient. Ooh, constant. It's 0. It's 0. It's not there. What? See, constant is the number without a variable hooked to it. Graph this on your calculator and tell me what it looks like, huh? Yeah. It absolutely is. It's the biggest one. It's the first one if it's in standard form.
It's going to be a backward F.
It's
going to be a backward F.
Okay, I don't know that I would.
No, that is not it. That's not it.
Zoom in some on it.
No, she's right. No, you're not. You're not right.
Zoom in some on it. Go to window and do -5 to 5 and -5 to 5. Okay. I believe you. I could put it on my calculator, but I can't see the stupid little thing. Okay, there we go. That's fine. That's fine.
I knew it.
Does this one have a max or a min? Why? It's not a straight line, but it's always increasing as I move left to right. In order to have a max or min, I have to stop increasing and start decreasing, or vice versa, right? And it never does. It's always increasing. How about zeros? How many zeros does it have? 1. It has 1 0. That 0 happens right here. Okay. What about in behavior? Yeah. You're talking about those graphs where it said look at it? I got to fix my camera and then I'll show you. For some reason it's not working, so I just decided not to fight. Yes, because it's going, this says on the left side it's going down. Can you make a general in behavior statement? In other words, without graphing the polynomial, can you know it's in behavior?
Yeah.
How? Okay, let me give you an example. I'm talking about in behavior though. Could you tell me about in behavior on this one without graphing it? All right, hold on. As x approaches negative infinity, what did you say it does? Sure. So it's infinite. That's right. That's right. So
I wouldn't have been able to do that.
I know. We know. There you go. That's what I wanted you to remember, is we're looking at the degree compared to the leading coefficient, and we're using that to classify the in behavior. Do you remember we did a little chart? I am. Yep. We're making a little chart here. What is that? What are you doing? I'm making. All right, we've got a chart here with 4 different scenarios. This is what's going to determine my in behavior. If you remember this from Algebra 2, that's wonderful. Jackson does. That's awesome. If you don't, we're just going to fill this chart out really quick. I won't spend as long on it as what I do in Algebra 2. I'll just give it to you and tell you what it is that's happening. But every single polynomial that is an even-degreed polynomial with a positive leading coefficient has the exact same end behavior. Okay? All even degrees, the ends go the same way. Think about a parabola. They're either both going to go up or both go down. If it's a quartic, same thing. Both up, both down. Any even degree has the same end behavior on both ends. You just have to determine which it is. So if it's positive, think about a parabola that goes up. What's the end behavior look like there? That's exactly right. How about the other end? The opposite? There you go. Okay. Any polynomial that you find that has a positive leading coefficient and an even degree is going to have that same end behavior. So you don't even have to graph it, you can just know. I'm going to do the opposite on the negative because if it goes down, that means the only thing that's changing here is the ends here are going to be negative. So if you can literally think of one basic example to fit that criteria, which I think that's what Jackson was doing, you can determine what the end behavior of any polynomial is going to do. Let's look at the odd degrees. How it's related to what graph? Any even degreed polynomial, if you graph a quartic, the biggest exponent, okay? Any even degreed polynomial, both ends are going to go the same way, period. If you graph them, they just are. It might even kind of flatten out like this and do that, but they're going to go the same way. If the leading coefficient is positive, they both go up. Think about a parabola where that a is positive and they go up. If it's negative, it's going to go down. That's true for any polynomial in the whole world. Then if I'm odd, well, odd has opposite end behavior. So what's the most basic odd degreed function you can think of? Okay, well, I was trying to get you to get here because a line with a positive slope, but whatever helps you, but the ends are going opposite, okay? So as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x is going to negative infinity. Yeah. We're actually fixing to talk about that, but that's your one less than the degree. Yeah. That's the minimum, that's the maximum number of critical points of maxes and mins. Yeah, that's for even and odd. That's a general polynomial thing. And then, of course, if it's odd and negative, this is what it looks like. Or maybe it's a cubic that does more like that, right? It doesn't matter. The ends are just going negative, going opposite directions. So as I go to positive infinity, this time the graph is going to go negative. And as I go negative, the graph goes positive. I'll give you a second to catch up. This is just like a algebra 2 repeat. Why can't what? Do what all the time? What, algebra 2 repeat? Because we're in pre-cal now. You didn't like algebra 2 when you were in there. No. So now you want to go back. All right, so Robert, you said how did he just know that? I'm sure in your head, Jackson, you can tell me if I'm right or wrong, but is that what you did? Did you think of an odd degree up to like a line, what the ends were doing? He got it right. That's an odd number. So it should have opposite. Is the leading coefficient positive or negative? So negative odd. No. No, I just wrote them backwards. I did negative first. He's right. It goes positive, negative, positive, negative, negative, positive, negative, positive. He's right. It doesn't matter which sentence you write first, as long as the positives and the negatives go with each other.
Same.
All evens are same. It's really, if you think about it, it's not hard to remember. You just got to think the odds are the hardest. Evens are the same. Evens positives are both up. Evens negatives are both down. Odds are opposites, so think about a line. If it's positive, then it's positive, positive. But if it's negative, it's positive, negative. Go okay? So now, instead of writing our end behaviors this way, I'm going to change it up on you just a little bit. We're going to use limits to write our end behavior. It's okay. It's actually a little bit easier to write. If I want to say that as x approaches, did you? You don't have an old school. What? You're getting me all mixed up. All right. When we use limits to describe the end behavior, what we do is we say the limit as x approaches infinity. Okay? So when we talk about limit, we're talking about a number that it gets really close to. So the limit as x approaches infinity of f of x equals, well, what's it going to? The closer x gets to infinity, if I'm saying this, negative infinity. So we could rewrite all of these using limit notation. Yep. It's not useless. It's what you knew before. Now I'm showing you a new way to write it. Yeah. Every time, listen, I put something old up here and y'all like, yeah. Then the first new thing that goes up, this is stupid. What the heck? We read this as the limit as x approaches infinity of f of x equals negative infinity. Yes, this and this are the same thing. Every single day. Calculus is doing limits right now. Calculus is doing limits right now. So let me show you. So I'm going to come here beside this chart, and I'm going to write these end behaviors in limit notation so that you see. So this first one is the limit as x approaches infinity of f of x equals infinity. And the limit as x approaches negative infinity of f of x. Well, I didn't want to do a whole nother chart because then y'all will fuss about that. Okay. Even, positive, even, negative, odd, positive, odd. Y'all, this is not. All right, think about up.
Almost you stop. This is nothing.
The limit as x approaches infinity of f of x equals what? There's one end. That's the right end.
Infinity.
Yes, they're both going to be infinity.
Oh, there's a fight.
That's not a fight. You think?
Gang, wait. What's the bottom limit?
It's
Is the bottom one x goes to negative? On the two black ones.
I don't know what you're talking about.
Are they both the same for the bottom?
No, not for the bottom.
The bottom has a negative in front of it? Big old black? Black. Under the second limit.
That's positive. Oh no, that's negative. That's negative. It just over. Sorry. Yeah, sorry. Shut up now. Right now. Not another word. Just shut up.
This is all we do.
Does he laugh?
No, it's like, yeah. William started talking today.
Say that one more time, Aiden. Hold on. No. Odds or opposites?
Today, William started talking to just yelled
Hold
out.
on, let me fill it out.
That's a write-up. No. You started talking about dubs. And like,
Both of these are going down, so both of these are negative. This one, the positive end is going up, the negative end is going down. This one, the positive end is going down, the negative end is going up. So now this will be the expectation for the way you write your end behavior instead of as x approaches. All right. Well, because we start in calculus, we start using limits a lot for the actual definitions of asymptotes involve limits. And so that's where, well, then you should take pre-calculus because this is the intro course to calculus. Literally in the name, it's pre-calculus. That's like saying, I'm in pre-algebra, but I'm never going to take algebra. All right. What are zeros?
It's a number between positive and negative numbers.
X-intercepts, where it crosses the x-axis. What are extrema? Maxes and mins. So, if you have a polynomial, if your degree is n, because that's what we've been using for all of our polynomials is a degree of n, right? Then I have, if I say this, do y'all know what that means? Less than or equal to, so no more than this number. N zeros and n minus 1 extrema. If you think about it, it makes sense. If I have a cubic is a degree of what? So if I have, it's saying this polynomial, without graphing it, I know has no more than 3 zeros, no more than 3 zeros, and no more than 2 extrema. That's exactly right. Because I just told you. I haven't found them. I'm not finding them. I'm just telling you. And it makes sense because if you think about what a cubic looks like, the most number of times it could ever cross the x-axis would be 1, 2, 3 times, right? I can't have any more than that. Yes, it is. It depends on how you start stretching and shrinking it. But I'm saying the most it could ever have, there's no way to stretch it, shrink it, shift it, move it, flip it, anything where it would have any more than 3 zeros. That's the most. There's no way that anywhere on here I could stretch, shrink, or flip this where you'd have more than 2 humps on here, 2 maxes or mins. There's no way. So that's the most number. That's a very important theorem that we use a lot. No, because this could be just f of x equals x to the 27th plus 3. Well, then that would tell me I have no more than 27 zeros and no more than 26 maxes or mins. One less than the degree. It's always one less than the degree. Yeah. I got one more thing to tell you, and I'll shut up. We talked about when you were in Algebra 2. Okay, we're still on zeros here. They're like copying his notes. Like, I'm not gonna say anything because I'm just glad you're taking notes. Algebraically, when we found zeros, right, we talked about, we factored and solved, right? Most of the time we'd get it down to something like this. And we'd say, well, x equals -2 and x equals 1, right? That's a quadratic that's showing me 2 solutions. But what if I had and we talked before that these are what we call, well, you wouldn't have to because it's written 3 times if I'm just talking about zeros. These are what we call repeated solutions. Because -1 would happen 3 different times, right? The number of times it's repeated is what we call the function's multiplicity. So, no, stop. This is a fancy word for how many times it's repeated. So, I have a 0 here of x equals -1 with multiplicity 3. Did we do it? Did we talk about bounces and passes through? Did we do this in Algebra 2? Wow. Okay. Wow, go me. I got to that in Algebra 2? Yeah. You're right. It's even. That's exactly right. This is the multiplicity, James. That's all. However many times it was there. Yes. So then x equals 4 is a 0, and its multiplicity of 2. If your multiplicity, remember, these are zeros, it's where they cross the x-axis, right? Or where there's a point on the x-axis, this x-intercepts. If your multiplicity is even, this is going to be so much easier since I've already taught y'all. Huh? Yeah. Even multiplicity bounces off the x-axis. For example, if y'all already got that in green. So if I had, for example, f of x equals x minus 1 squared. The 0 here is 1. Do you agree? X equals 1 is a solution. Its multiplicity is what? 2. That's even multiplicity. That means here, this just goes, it bounces. It touches the x-axis and bounces right back up. Every even multiplicity will do that. Multiplicity 2. Because it happens twice. X minus 1, x minus 1. See the equation? Yes, because what you're doing is you're saying you're setting it equal to 0 and you're solving. So x equals 1. This tells you what your zeros are doing. If they're going straight through the x-axis or if they're hitting the x-axis and bouncing back up. Right. If it's odd multiplicity, it goes straight through the x-axis. So let me show you on Desmos, it'll be easier. Oh, Carter. Let's say x minus 3. I'm going to raise the, oh. Where did I what? And x plus 2. What should be happening here is because positive 3 has got an odd multiplicity, it should be going through the x-axis there, and it should be bouncing at negative 2 because that's an even. What are you doing right now? No, that doesn't embarrass him. No, he's done something else. Do y'all see what I'm talking about? Even multiplicity, because it bounces, it touches it and bounces. It literally hits it and it's gone. This one goes straight through because it's odd multiplicity. It's got a multiplicity of 5. See, whenever it hits 5, it doesn't bounce off and go the other direction. It keeps going through it. This one touches it and then goes nope and goes back the other way. Harder. Okay, I'm going to stop there because I've lost.